recording. Okay, good evening, one and all. So today's topic for discussion is we are going to discuss all the units. I simply go through the overview of those units. I think that already we finished 4 units in face-to-face interaction during classrooms, and only 2 chapters were remaining. I think that already I have shared all those videos. I don't know how many of you have gone through the videos and have listened those videos. Okay, so today's discussion is all about to make you aware of all those 6 units and the set of steps that you should follow for while studying the computer organization and architecture course. So let us start with the simple figure I will go through and will make you understand. Okay, so here you can see the figure. In the very first chapter, I discussed this particular block diagram. So let me repeat it again. Here you can see there are basically 3 blocks. The very first block is central processing unit. This particular block is called as the processor. And as we already know, the processor is basically divided into 2 sections. One is program control unit and second one is data processing unit. The role of program control unit is to fetch the instruction from the memory. So here you can see there is a arrow from memory and it is connected to program control unit. And once the instruction is fetched from the memory, it is to be decoded and some control signals are generated for data processing unit for further execution. And if you look at the another unit, that is data processing unit, this unit is basically responsible to execute the instructions. Behind screen, you can also understand that only execution is not there. So it requires some kind of registers, operands value. Those may be located in the register or it may be located in the memory also. So here you can see, so required data is fetched from the main memory, and again once the execution is over, again the data is again copied to the main memory. So 2 directions, 2 arrows, bi-directional arrow is there from main memory to the data processing unit. One more unit is there, that is a main memory unit. Let me review the points. See, in the very first chapter we discussed the generations. See, we discussed first generation, second generation, third generation, fourth generation, and we also discussed, if you remember, there is a highest computer, and that was discussed in the second generation. So the basic idea in the first chapter is to understand the basics of computer, like main memory, central processing unit, input output equipments. And in the second chapter, actually we discussed input output organization. So how the input output is organized, how the input devices and output devices are connected to the system bus. As we already know, whenever we press any character on the input, how the processor came to know that someone has pressed the character and associated code is loaded into the status register. So all those things we discussed in the input output equipment, input output organization chapter. This is our chapter number 2. In the chapter number 3, we focused on again the data processing unit. You might aware that in the data processing unit there is a one ALU unit, and the responsibility of that unit is to execute the instructions. It may be addition, it may be multiplication, division, or it may be any kind of arithmetic operations can be done in the data processing unit. And in the unit number 3, we discussed in detail how that particular unit is designed and how the multiplication is carried out. In the multiplication also we discussed both multiplication algorithm. Then we discussed the binary bit pair recoding technique. And we also discussed how exactly the floating point numbers are to be stored in the memory. So if we move further in the chapter number 4, again we are going to discuss in detail about this data processing unit. Now, what is the role of data processing unit? We already discussed that data processing unit may contain the list of registers. So there may be the register file, it may be a accumulator, it may be a data register, and along with this, there is a one unit called the arithmetic unit, ALU unit. So in data processing unit, we are going to discuss how those registers will help to the ALU to make available those all values which are required for the processing. So this chapter is basically dealing with internal part of data processing unit, and it is totally related to the execution part. After that, in the unit number 5, we are going to go for pipelining. Now, before I go for pipelining, let me tell you that before that unit we discussed the computer memory system in the unit number 6. Now, what is the role of this computer memory system? In the memory system, we discuss how the memory is organized. Means, as we know, the memory is basically divided into a number of cells, and each cell can hold the 1 bit of data. We also discussed the various architectures also, 16 by 8 memory. We also discussed the use of cache memory, why the cache memory is required for the processor, because the cache is very close to the main memory, and the request of instructions is satisfied in the single clock cycle. So we also discussed the hierarchical structure of memory, like first very close to the processor is a register. After that, there is a cache memory, then there is a main memory, and there is a secondary memory. We also discussed the various cache operations, cache miss, cache hit. So everything we discussed in the main memory, and ultimately the goal of this main memory is to store the instructions as well as data, and collectively, I would say nothing but the program. So program is collection of data and instructions. The role of processor is to fetch those instructions one by one, made it available to program control unit. Program control unit will decode it and generates the control signal to data processing unit, and data processing unit will further execute the instructions, and if it requires, again result back stored into the main memory. Now, what is the concept of pipelining? Pipelining is a one kind of technique. You might have remembered that we discussed the speed up technique of processors. There are three different speed up techniques. One is use of cache memory, and there is a pipelining. Because of pipelining, we can simply organize the instructions in such a way that the time required for execution is reduced. Okay, and so this is somewhat the overall structure of computer organization and architecture course. So you always remember this figure. There is a link between each and every unit. We are going in detail in every chapter. So today I'm going to touch up with pipelining concept. So let us move further for the discussion. Uh, Wait a minute. Let me see your suggestions. Okay. Okay. Can anyone hear me? Yes. Hello. Hello.
Yes, sir.
Who is speaking? Yes. Hello.
Srinidhi, sir.
So as
Hello.
I discussed a few points to with you, uh, have you understood? Yes. Hello.
Yes, sir.
Hello.
Yes, sir.
Okay. Okay. Fine. Shall I move further? Yes.
Okay, sir.
Okay.
Okay,
Fine.
sir.
Fine. Okay. 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 So let us go for the discussion of pipelining. Um, So I simply touch up four important points of pipelining here. Simply we go for basic concept, and then we we are going to discuss the role of cache memory for pipelining. Then we shall go for discussion of some performance of pipelining. What kind of strategies are used to improve the performance. And last, we are going to discuss the hazards. So let us discuss one by one. So let me first discuss the basic part, basic concept of pipelining. Here you can observe there is a sequential execution of instructions. So at a time in memory there are so many instructions, and here you can see, as we know, we are, for only sake of simplicity I am considering the 2 units, but basically instruction is executed in 4 stages. First the instruction is fetched, then it is decoded, some operands are loaded, then executed, and again the data is stored to the memory unit. So here I am considering only 2 units. One is a fetch and second one is a execute. So if I want to execute I1, this instruction 1, the processor requires 2 cycles. F1 for fetching the instruction, and for executing I need one more cycle. So 2 cycles are sufficient for the execution of instruction 1. After execution of instruction 1, it simply fetch the next instruction, that is I2, and again it requires 2 cycles for completion of that instruction. So this kind of organization is called as a sequential execution. Now let us calculate how many cycles are required to execute these 3 instructions. So for I1 I need 2 cycles, for I2 I need 2 cycles, and for I3 I need 2 cycles. So 3, 2 plus 2 plus 2, so 6 cycles are required for the execution of 3 instructions. Now can I reduce this time, or can I reduce the number of cycles so that the processor speed is increased? And here the concept of pipelining comes into the picture. So here you can see in the next figure, this is a one kind of hardware configuration or organization. So whatever the instructions are to be fetched, whatever the output of instruction fetch is stored into the internal buffer, and it is basically called as an inter-stage buffer, because we are having 2 stages here. Stage 1 is instruction fetch unit and stage 2 is execution unit. So whatever the output generated by the instruction fetch unit is kept into the what? B1. B1 indicates the buffer. So buffer is a place where you can keep your data temporarily. And again from the buffer, execution unit will further proceed with the content of buffer unit, as uh, the input is made available from the buffer to the execution unit, and the execution is started. So let us apply the pipelining concept here. So instruction 1, instruction 2, and instruction 3. So every instructions required 2 phases. Means 2 units are there. The F1 unit means F1 stage is responsible to fetch the first instruction. This is the clock cycle. So in the first clock cycle, F1 stands, the first instruction is fetched. In the second clock cycle, here you can see F1 is now free, and here E1 stands, the first instruction is executed, and at the same time the second instruction is fetched, because in the second clock cycle fetch unit is now ideal state. Now you can use fetch unit for fetching the next instruction. And in the clock cycle 3, here you can see E2 and F3 means here second instruction is executed and third instruction is fetched. And if you move further, so here you can see the first instruction is finished in the second clock cycle, end of second clock cycle. Second instruction is finished in the end of third clock cycle, and third instruction is finished in the end of fourth clock cycle. So if you compare how many clock cycles are required in the pipelined execution, here you can see only 4 clock cycles are required for the execution. But if you see here in the sequential execution, we discussed very few minutes ago, we require 6 clock cycles. And this is a concept of pipeline. So let us move further for the next point. So anybody can hear me? Yes? Have you understood? Yes?
Yes, sir.
Shall I move further? Hello?
Okay, sir.
Okay, fine, fine. So let us move further. Uh,
सर फक्त तुमचा आवाज थोडा मध्ये मध्ये बफरतोय.
Actually, through mobile, through WhatsApp, I have started the session. It may happen because of some internet connectivity problem and also range problem. Uh, Actually, I am recording the session. Once I finish it, I will make available the same recording. Okay. So let me move further. Uh, okay. As we discussed, uh, actually I had taken only 2 phases for demonstration, but every instruction requires 4 phases, 4 stages. Sometimes I can also call as 4-stage pipeline. So phase is responsible, as we discussed, with the instruction from the memory, and again decode the instruction and fetch the source operands. So these two things are carried out in the same phase, in the decode phase. After that, execution unit is responsible to perform the operations specified in the instruction. And finally, once the execution is finished, the operands are again kept into the destination location. Now, destination, either it may be the register or it may be the memory location. So let us discuss the role of cache memory here. The problem is that we know that if the instruction is very close to the processor, it requires only one single clock cycle. So there is a memory hierarchical structure. Means first there is a register, then there is a cache memory, then there is a main memory, and then there is a secondary memory. So if requested data, if it is available in the cache memory itself, because register may not hold the large number of instructions. So if the requested data by the processor is available in the CM, means cache memory itself, the request is satisfied in a single clock cycle, and ultimately the time is reduced. But if the requested instruction is not available in a cache, means cache miss is occur here. Cache miss means if the data is not available in the cache memory, the request is made satisfied from the main memory. So first, that particular instruction is brought from the main memory to the cache memory, and then it is made available to the processor. So obviously it takes time. So the role of cache memory is very important to improve the speed of processing. See here, I simply show you the only the stages of pipeline here. The 4 instructions are there. So if you look at here, D1 phase and F2 phase are overlapped. So this is a partial overlapping. This is nothing but the partial overlapping. So these 3 stages are overlapped in the cycle number 3. These 4 stages are overlapped in the cycle number 4. Now you may wonder, sir, every time we requires how does it possible that every phase requires a single clock cycle? So this is the one kind of ideal case I'm considering here. Means here instruction execution is divided into the 4 steps. Means I am assuming that every instruction requires 4 phases, or the each instruction will finish in the 4 clock cycle. If you look at the instruction number one, it requires how many clock cycles? Yes, it requires 4 clock cycles. See here, 1, 2, 3, and 4. Similarly, if you move further, again the instruction 2 is requires again 4 clock cycles. Instruction 3 requires again 4 clock cycles. Instruction 4 requires again 4 clock cycles. But it may not happen all the time, because it may happen that execution unit E1 may require the data which is not available in the register, but it is available in somewhere in the main memory. So here, in order to fetch that data from main memory to the register, it takes one more extra cycle. So always remember, so how we can speed up the processor. If we use the cache memory concept here, the request is satisfied in a single clock cycle and the data is made available to the processor within single clock cycle, and the access time is automatically reduced. So here you can see the hardware organization of these four stages. The very first stage is a fetch. Output of fetch is kept into the buffer. These are basically called as interstage buffers. Buffers are basically the temporary blocks where the result is kept. So output of fetch is kept into the B1. It is made available to decode unit. Again, the output of B1 decode unit is kept into the buffer B2. It is made available to the execution unit. And further, so it means if there is a four-stage pipeline, I need three interstage buffers. So the role of cache is very important as far as the execution of instruction is concerned, because we cannot think the ideal case all the time. It may happen that every unit may require extra clock cycles for the execution, for the decode, for the fetch, likewise. So let me tell you, let me discuss the various hazards here. Hazards is a one kind of concept where it is a one kind of condition that causes the pipeline to stall the clock cycle. Stall इसका मतलब ये है कि यहाँ पे जो अभी प्रीवियस स्लाइड में हमने पढ़ा कि भाई एक इंस्ट्रक्शन को मैक्सिमम 4 साइकिल लग सकते हैं, बट इट इज नॉट आइडियल केस. यहाँ पे क्या हो सकता है कि each unit may stall the cycles, means each unit may require the extra clock cycle which we assume as a one clock cycle, and this kind of condition is basically called as hazard. ये ऐसा एक कंडीशन है कि जिस कंडीशन में यहाँ का कोई भी यूनिट, अगर हम यहाँ पे देखेंगे, आइदर इट मे बी फेच यूनिट, डिकोड यूनिट, यहाँ पे एग्जीक्यूशन है, राइट यूनिट है, तो यहाँ पे कोई भी यूनिट एक्स्ट्रा क्लॉक साइकिल ले सकता है. और ऐसा कोई भी कंडीशन जो क्रिएट करता है कि भाई एक्स्ट्रा क्लॉक साइकिल लेना पड़ेगा, उसको हम बोलेंगे हजार्ड्स. So there are basically three types of hazards. First, there is the instruction hazards, then there is a data hazards, and there is a structural hazards. So here you can see the concept of data hazards. So what do you mean by data hazards? Any condition in which either source or destination operands of an instructions are not available at the time expected in a pipeline. So what time we expected in a pipeline? For every stage we have given only one single clock. But in the single clock cycle, that data is not made available for the execution purpose. So here we require extra clock cycle. So if you look at here, as a result, some operation has to be delayed and the pipeline stalls. Pipeline stalls means what? That particular stage requires extra clock cycles. Okay, fine. So I think that let me show you the example here. So instruction I1, it is a one I'm considering here is a one ideal instruction, because instruction is fetched in the single clock cycle 1. It is then decoded, then executed, and then results are again loaded to the memory or into the register. But if you look at the second clock cycle, in the clock cycle 2, in the clock cycles 2, I2, instruction I2 is fetched, and first instruction is decoded. And look at this part. So E2 requires, actually we decided to execute this E2 in one clock cycle, but it requires how many clock cycles? From 4 to 5 and again 5 to 6. So Instead of one clock cycle, it requires extra one clock cycle. Why this happens? Because the execution of instruction I2 requires a data, this operand value, which is not available in a register, but that operand value is available somewhere in a memory. Hence, it requires first the data is made available into the register, and then it is to be given to the execution. So one extra clock cycle is required, and now this condition is basically called as data hazard. Because of what? The data is not available in a source operand or the destination operand. Data is not available in the register. It is somewhere available in memory. That's why the delay happens, and hence we require the extra clock cycle here. So this is the case of data. And because of this, as E2 is not ideal till 6th clock cycle, remaining. So here E3 is now extended, because we cannot execute until and unless the execution unit is free in the instruction 2. So that's why if you look at this portion, so this execution unit of I3 is postponed, because uh, till now, in up to the 6th clock cycle, this particular unit is used by what? Instruction I2. So this particular type of hazard is called as a data. Now let us try to understand the next hazard. So this is an example of instruction hazard. As we discussed, as I told you, there are three kind of hazards conditions. Because of that, pipeline may stall the cycles. So here you can see. Let me make one situation here. See, we are having the register first, then we are having the cache, then we are having the main memory, and then there is a hard disk secondary memory. So let us consider the processor is here, and you might aware that these two units, means register and the cache, both are located on the same chip where the processor is located. That's why the instruction, if instruction is available in the register, it is to be satisfied in a single clock cycle, and if it is available in a cache, it is again satisfied in a single clock cycle. Now let us look at this example. Instruction I1 is a very ideal case where all the units are getting only one clock cycle here, and instruction I1 is executed very smoothly. But if you look at here, instruction I2, so at the second clock cycle, first instruction is decoded, and second instruction is taking how many clock cycles here? 2 to 3, 3 to 4, and 4 to 5. It means it should finish in the single clock cycle, but it requires two extra clock cycle. Why it so happens? The reason is very simple, as we discussed the situation here. As the instruction is not available in a cache, that's why it is available in main memory. So first the instruction is loaded into the cache, so it takes one clock cycle, and then from cache it is made available to the processor, so it requires extra one clock cycle. So hence two clock cycles are required. So due to delay in the availability of instructions, the pipeline stall the clock cycle. Hence it is called as instruction hazards. So you can also understand the same. This is the situation where cache miss occur. Cache means what? Requested data is not available in a cache, so cache miss is occur, and it is made available from the main memory. So this is another kind of organization. The same is to be organized by another way. So these are the clock cycles. These are the units: fetch, decode, execute, and write. And see here, whenever in the clock cycle 3, you can see here clock cycle 3. So ideal. What is the meaning of ideal? We cannot move further. We cannot move further because the phase 2 is still in a progress mode. So in the clock cycle 3, execution unit means first instruction I can execute, but second instruction I cannot execute because it is not second instruction is not fetched because still it is made available from the main memory to the cache. The same scenario is for clock cycle 4. In clock cycle 6 also there is the same scenario. Clock cycle 6, so the fetch is finished of the second instruction. Now I can decode it. Likewise, the same is to be organized in another way. Let us move to the next hazard. So this is the last type of hazard where this is a one kind of deadlock situation. You might have studied in the operating system course that if two instructions are required to use the given hardware resources at the same time, then the structural hazard will occur. So for understanding purpose, I have taken one simple example here. This is a one kind of load instruction. And if you see here, the source is of type indirect addressing mode. You might have studied the various kind of addressing modes in a microprocessor. There may be the immediate addressing mode. There may be a direct addressing mode. Immediate means in the instruction itself, the data is given. In direct addressing mode, it is made available in register. Indirect addressing mode. So this is a case of indirect addressing mode where there is a somewhat the memory X, and that memory, if you go that memory, there is a register R1, and then the register R1 is holding some kind of data. So if you look at this instruction, I1 is again taken as a very ideal that each and every unit takes one clock cycle to finish its task. And now for load instruction, if you look at here, the first instruction is fetched, then it is decoded at the time of execution. So execution unit requires the operands, and the one operand is available in register, means I have to load the content of this register to somewhere to the R2 register here. So E requires the value of somewhat the memory location X where the register R1 is located and from where I'm getting the value. So for execution purpose, I have to first load the memory. Load the memory means what? Contents are first loaded. So if you look at here, as we discussed so far, that execution unit takes single clock cycle, but it may not be ideal all the case here because execution, before execution or for execution, I have to first load the memory. So here the execution unit is taking one extra clock cycle. And now come back to the instruction I3. Here the F3 means instruction 3 is fetched in the clock cycle 3. Then it is decoded in the clock cycle 4, and then it is executed also, but it may not write. Why it may not write? Because in the instruction I1 it takes one extra clock cycle, and here the still the write unit is not free because instruction I2 has not finished his activity of writing. So means these two units are now trying to access, means these two instructions are trying to access the write unit at the same time. And because of that, this instruction I3 is skipped, or first this instruction is executed and then this instruction is executed. So here in the instruction I3, one extra clock cycle is required, or it stalls one clock cycle because of this particular structural hazard. So we are now ended with the discussion of hazard. Now let us go for the discussion part.